The topic is ideal and non-ideal solution, and this category is usually studied from the subcategory known as completely miscible solution. To have solutions of this category, we have to take both polar liquids, means the solute and solvent should be polar and polar, or we can make a solution with non-polar and non-polar mixture. When such liquids are mixed, they form only one phase. So in order to differentiate between ideal and non-ideal solutions, some of the following categories or criteria are taken into consideration. So first one is, if the forces of interaction of the components after mixing are same as the among the molecule of pure components, then the solution are ideal. For example, if we have component A which is mixed with B, overall after mixing we have new types of interaction, that is A is interacted with A, B interacted with B, and A is interacted with B. So all these type of forces must be similar as observed among the molecule of pure components A and B. It means that if A-B interaction is present, then the solution is considered as non-ideal. And if the solution have previous interaction, that is AA or BB, so this kind of interaction present in the solution, that solution is termed as ideal one. Number 2 is heat of solution must be 0. Then the solution is ideal. And if the heat of solution is non-zero, then the solution is non-ideal. It means when two components are mixed together, there isn't any evolution of heat for the case of ideal solutions. Change in volume, that must be 0 for the case of ideal solutions. It means if there is no change in the volume of the solution, then the solution is ideal. If this change in volume is positive or negative depending on the forces of interaction, for new stronger forces, delta V is positive, and for new weaker forces, change in volume is negative. It means that for the ideal case, when we have volume V1 of one solvent and V2 of the solute, the total volume should be equal to V1 plus V2. It means change in volume is 0 for the case of ideal solution. But for the case of non-ideal solutions, we have change in volume either positive or negative depending on the development of the new forces that are stronger or weaker. These forces developed are known as intermolecular forces. These intermolecular forces depend on the type of the liquid. If you are taking polar solvents, then the forces can be either hydrogen bonding, depending on the hydrogen bonding, depending on the availability of the more positive hydrogen atom, and they can be either dipole-dipole interaction or London dispersion forces. For example, if you mix water with ethanol, there are two types of existent forces in water, that is hydrogen bonding and dipole interactions. And similarly, ethanol have its own forces of attraction. When these two liquids are mixed, for example, if you are taking 20 ml of water and 20 ml of ethanol, so overall solution must have 40 ml volume if it is considered as ideal solution. Is negative, it means that the new intermolecular forces which are developed between ethanol and water are stronger than the forces of interaction between ethanol or water-water interaction. Next and most important criteria is those solutions which obey the Roult's law. At all concentrations and all the temperatures, and they are called ideal solutions. Roult's law is one of the best criteria to check whether a solution is ideal or not. So in order to understand the difference between an ideal and non-ideal solutions, let's thoroughly understand the Roult's law. We know that vapor pressure is one of the basic properties of a liquid. It increases with the increase in temperature. When solutes are added into the solvents or added into the solvent, the vapor pressure that is above to the surface of the solvent is lowered. It means this lowering of vapor pressure is due to the presence of the particles of solute present in the solvent as well as on the surface of the solution. It means the surface of the solution is stretched due to the solute particles, and the vapor pressure of the system is decreased as compared to the vapor pressure of the pure solvent. So if we have P1 for P2, and the change in vapor pressure is lower. So Roult's law has given the quantitative relationship between the vapor pressure of the solution and the quantities of the solute and the solvent. Let's consider that the vapor pressure of the pure solvent is P0 and that of the solution is P. That is solution and this one is solvent. and let the mole fraction of the solvent, mole fraction is x1 and for the solute is x2 respectively. And according to the definition of the Roult's law, the vapor pressure of the solution is directly proportional to the mole fraction of the solvent. It means that the vapor pressure of the solution is directly proportional to the mole fraction of solvent. So if you replace the proportionality constant, the vapor pressure of the solution will be equal to the vapor pressure product of the vapor pressure of pure solvent into mole fraction of the solvent. Since we know that the mole fraction of the solution is equal to 1, it means sum of the mole fraction of each component is equal to 1 for each solution. From this equation we can get the value of mole fraction of the solvent, that is 1 minus x2. So here we have equation number 1 and equation number 2. So by putting the value of mole fraction of solvent in equation number 1, we get through rearrangement So here we can say that the vapor pressure of the pure solvent is higher as compared to the vapor pressure of the solution. So this value can be written as change in vapor pressure, that is equal to P naught x2. So we can say that change in vapor pressure of the solution with respect to vapor pressure of the pure solvent is directly proportional to the mole fraction of the solute. So here we can see that the vapor pressure of the solution is directly proportional to the mole fraction of solvent, whereas change in vapor pressure is directly proportional to the mole fraction of the solute. So the lowering of vapor pressure delta P is directly proportional to the mole fraction of the solute, and this is you can say the second definition of Roult's law. So equation number 3 is rearranged as change in vapor pressure with respect to vapor pressure of the pure solvent is equal to mole fraction of the solute. And this term is known as relative lowering of vapor pressure. So here we get the third definition. According to the third definition Roult's law, the relative lowering of vapor pressure is equal to the mole fraction of the solute. So according to this third definition of the Roult's law given in this equation, we feel that it should be better reported in the literature rather than the lowering of vapor pressure, because the relative lowering of vapor pressure is useful as it is independent of temperature. It means at all temperatures this equation is constant. The second significance is the relative lowering of vapor pressure is proportional to the concentration of the solute. And the third significance is is a constant quantity. The relative lowering of vapor pressure is a constant quantity when equimolar properties or proportions of the different solutes are dissolved in same mass of the same solvent. It means that if you take water 100 ml of 100 it's better to take in gram, 100 gram of water plus 100 gram of ethanol, and you add 0.1 molar sodium chloride and 0.1 molar potassium chloride into the water separately. Both sodium chloride aqueous solution and potassium chloride aqueous solution will have same value of this relative lowering of vapor pressure when the solvent is constant. But if you replace the water with ethanol, you will get the different value of mole fraction or different properties.